Okay, so instead I'm going to start recording this. Okay, so now we're being recorded, even though it might not tell you on Zoom. I'm telling you we are. So actually, no, you're not. It's just me because it's the pre-Zoom feed. So anyway, our plan this week is to have a little lecture today and think a little bit about tectonic geomorphology. That's what we'll do for our morning session. Um, We'll take a break as we always do for lunch. And then this afternoon, we'll start by having you watch a field trip video to Palouse Falls. Uh, this video is very, very recent. I recorded it yesterday. So yesterday was a pretty crazy day. I had meetings all morning and then got out for our field trip to Palouse Falls yesterday afternoon and then edited the video late last night. So it should be pretty much good to go. Got a good song choice for you on the intro this week. And as you'll see, interestingly, it's a field trip to Palouse Falls, but Palouse Falls almost isn't the main point of the field trip. As you'll see, we actually get there after dark, so there's a lot of interesting things we're going to see on the way. Now, the lab this week is essentially it's an extension of last week's lab. Last week we learned a little bit about kind of the regional landforms in the Walla Walla area. We thought a lot about the Missoula floods, and we looked at a field trip down the Walla Walla River Valley and trying to see where some of those floods were. This afternoon, we're going to go the other direction. We're going to, instead of going to the west, we're going to go to the north, and we're going to look at more evidence for floods, but not just depositional features like tushy beds. We're going to look at erosional features as well. But along the way, we're going to see some other really, really cool and important landforms that we need to understand and think about when kind of trying to understand the broad area around us. So that's the plan. An exciting note was that Paul and I made it to Dayton, and it was a nice bakery in Dayton. Has anyone ever been to the bakery in Dayton? No, it's there. It's across the street from the convenience store. Um, and they were closed, but we walked in anyway because I didn't realize they were closed, but they gave us an entire box of donuts. So Paul and I are both amped up and over sugarly loaded on over a dozen donuts between last night and this morning. Um, okay, and then so that will be our lab, and then essentially the turn in for this lab will incorporate kind of your work from last week and this week for a kind of a 2 week style of lab that you'll be turning in. Okay. That's it for today, and then and then on Friday we'll continue on with more tectonic geomorphology. That'll set us up for next week for our last week of class, where we'll talk about the topic that I'm really interested in, and that's paleoclimatology and how paleoclimatology relates to geomorphology. So that'll be our last week of class together. Okay, does anyone have any questions for me before we dive in? No? Okay, in that case, why don't we go ahead and get started? We're going to be talking right now about tectonic geomorphology. Sir. All right, we're going to be talking about tectonic geomorphology. And does anyone recognize the picture behind me up here? Yeah, this is our local Walla Walla Valley again. And so, to understand kind of even our landforms around us, we've talked a lot about wind and rivers for shaping landscapes around us, but tectonics are also an important aspect of understanding the landforms and what the landscape looks like here in Walla Walla. So I'll just circle in green. This is our Walla Walla River Valley, right? That extends down all the way to the Columbia River. Um, and we've talked about some landforms already kind of in the tectonics world, right? We had this ridge right here. It goes across the Columbia River, the Horse Heaven Hills. So that Horse Heaven Hills, that's a tectonic related structure. That's an anticline structure. But then sitting behind us, one of the things that make the Walla Walla Valley so livable is having some elevation behind us. Have the big broad uplift of the Blue Mountains. It extends all the way down into South and Central Oregon here, uh, behind us. those are the result of tectonic forces as well, an uplift, a relatively recent uplift that has created the Blue Mountains and created those steep V canyons that are classic, like Tiger Canyon or Mill Creek Canyon that you've seen. So that relatively recent uplift, and we can maybe on Friday talk a little bit more about that, is evidence of tectonic activity shaping the landscape around us here. So, okay, there's all sorts of evidence of tectonic influence on landforms. So here's just a picture of a ground surface that's been broken open. You guys can see where the ground's been cracked open here. And commonly you'll see this type of landform associated with active tectonic settings where you have faults and faults traces that intersect the surface of the earth and actually break the surface of the earth. So this picture is from your textbook, and it's a fault scarp on the uh, fault scarp in I think in the Himalayas. So we can have kind of tectonic scale geomorphology kind of at like an individual fault scarp, but we can also think about tectonic geomorphology from a much broader perspective as well, and thinking about entire kind of continental margins. So here's a place that's near and dear to my heart. These are the Aleutian Islands and the Aleutian Island Arc. And so right here is essentially a plate tectonic boundary um, that is separating the Pacific plate from the North American plate. And right here, we have a trench where we're subducting the Pacific plate underneath the North American plate, and we're creating an island arc of volcanic islands. And so the ones that we mentioned in class when we talked about volcanic geomorphology are the ones way out here. Those are the islands of Four Mountains where you saw a couple pictures of. Then right there is Mount Carlyle, one of the active volcanoes in the Aleutian Islands. So this broad scale morphology, kind of having this deep oceanic trench and then this archipelago that extends out into the Pacific Ocean, are the results of tectonic geomorphology in this subduction zone. So kind of another big area of big high relief would be the Tibetan Plateau, right? So the Tibetan Plateau that separates kind of the low relief plains of India from the high relief Tibetan Plateau. We know that this is also a major tectonic boundary, right? Where we've got the Indian subcontinent that's slamming into the Eurasian continent. I'll just put some relative arrows on here. And so we're creating a convergent boundary between two continental masses that's produced the highest mountains on Earth, Mount Everest, but also the highest elevated landform on Earth, the Tibetan Plateau, which sits at a remarkably high elevation behind the Himalayan range front. And so that's the result of tectonic forces producing a very high, low relief landscape right here behind the Himalayan mountains, right? So you get the high relief Himalayas, and then uplifted behind it is that low relief but high elevation Tibetan Plateau. Um, we can also have kind of intercontinental scale boundaries as well. And so where we have extensional settings and where plates are pulling apart, we can actually develop lakes. And so here we have an example from Africa, and we're pulling apart um, the continent here, and we're creating a rift. And so rift lakes are really common because as you basically have an extensional setting with normal faults, you'll create a closed basin, and all that water can accumulate. Um, and so rift zones, like in the East African Rift, are where continental plates are currently tearing themselves apart. Has anyone heard of any rifts closer to home here in North America? Carmen might have an answer. Have you heard of one closer to home?
Isn't the basin and range kind of one?
So the basin and range is where we have extreme extension, and we'll talk about that. Um, but it's not necessarily a rift where a continent was tearing itself apart. Anyone know what I'm getting at here? We actually have a failed rift. Sad. We can't do anything right in the United States. We can't even rift correctly. We have the Rio Grande Rift. Anyone ever heard of the Rio Grande River? The Rio Grande River, which originates in southern Colorado and flows smack dab through the middle of New Mexico, down into Texas, and forms the border between Texas and Mexico. The low point down the middle of New Mexico, where the Rio Grande is flowing, is an actual failed rift margin where North America tried to tear itself apart about 30 million years ago, and it failed. What a loser continent, right? Can't even rift appropriately. So these rifting events can create uh, really signature landforms in continental settings as well. And let's not forget that we can have uh, boundaries associated with transform boundaries where two plates are grinding up against one another. And this also, a transform boundary can produce distinct landforms. One of the most obvious is offset streams. So here we've got a stream that's flowing down. I think I'm going the wrong way on this. I think this is up gradient here, flowing down. Then the stream basically takes a couple of right turns as it's going down. And so this would make a rectangular, right? We learned about these types of rectangular networks in channel patterns before. And this is the result of essentially a stream flowing across a strike slip fault, and then you're basically elongating the stream along that fault zone right there. And so in transform settings, these offset streams are very commonplace. And of course, a great place to go see offset streams is also right here in the United States. Go down to Southern California and on the San Andreas Fault, and you can see wonderful examples of offset streams. Okay, one topic that I have to start with, if we're going to understand tectonic geomorphology, is a foundational concept that really starts outside the world of geomorphology, perhaps, and is something more related to tectonics, and that is the concept of isostacy. Give me a thumbs up if this is a term you've heard before in another class before. Okay, a lot of you have at least maybe heard this term isostacy before. Maybe for others it might be brand new. Perhaps if this is your second class in geology, this might be a new term. Especially if you take like environmental geology for your intro class with me. We just don't have time to get into this in too much great detail. But this is a really important concept. And to understand isostacy, we have to remember kind of the overall structure of the Earth. And let's do this from a geomorphologist perspective. We're not going to get into the 750 discontinuity or the MOHO or anything like that. But let's remember that if we think about the Earth is like an apple. And what's something with a core in the middle? What's everyone's favorite model for the Earth? What's that? Cartman?
Like peaches.
A peach. A peach is a great example. The Earth is like a peach. It has a very thin skin. It has a big squishy layer in the middle, and then it has a hardcore pit in the middle, right? And so the Earth is very much the same. It has a thin skin that we call um, the crust, and then it has a big thick layer in the middle that we call the mantle, and then it has a rocky and a molten core in the center. Now, important part here is that the crust, that thin skin on the outside, is it's dense and it's cool and it's sitting on that warm mantle that is kind of it's solid but it's gooey. It's kind of squishy. And so depending on the thickness of the crust, it's going to sink more into that mantle. And that's the concept of isostasy, is basically how much does that crust sink down into the mantle. Now, another way to think about isostasy is the classic block model that is what we're showing here. And that this is, I'm sure all of you have done this, right? You've taken your wood blocks into the bath before and played with them. And you'll note that depending on the thickness of the block, it's going to stick up different amounts. And so if you have a really thick block, it's going to stick up more than a really thin block here that is sticking up less. And so that is the basic concept of isostasy, is that when essentially the crust is depressed down into the mantle, depending on how much crust there is, or if you stick something else on top of the crust, it's going to squish down more. That's our foundational, fundamental concept of isostasy. Okay. Um, And interestingly, right, if you start, if when next time you're in the bathtub, you can try this. Bring your wood block with you and bring your knife for whittling. Okay, and so what you'll do is with your block, I want you to measure how much of your block is out of the water, and then start whittling and cutting material off the top of the block so that it gets to be a smaller and smaller block. Now I want you to see where that line is for how much of the block sticks out of the water. You'll notice that as you shave off bits of the block, you'll end up with less of the block sticking in the water, and that's key for understanding isostacy. Of course, this is also the reason, and this is an important foundational geomorphology, that the fact of why we have oceans and continents at all is that you have oceanic plates and continental plates, and oceanic plates are made of basalt, and so they're denser, and so they sink more down into that mantle than the less dense continental plates. That's one reason why we have kind of ocean basins to begin with, is isostasy density differences types of crust. Okay, now that we've got isostasy down, we can move on here, think about this and why it's important from a geomorphology perspective. That's because if we want to understand the uplift at the surface, like how much a mountain range is going up, we're going to have to understand some foundational concepts like um, um, uh, uh, isostasy. So here's a very basic equation for how we can quantify surface uplift. So surface uplift is going to be equal to the amount that the rocks are going up. So that's our rock uplift, and we can think about these in terms of rates and meters per year, minus erosion, right? So if you've got a mountain range, the mountain range is going up, that's your U sub R. But what's also happening is, by all the delightful processes we've learned about in this class, right? Glaciers, debris flows, our mountains are also being eroded and being eroded down, and that is our erosion rate. And so if we want to know that net how much our mountains are going up and down, how much that mountains going up and down, we have to balance our uplift versus our erosion. That's key for understanding uplift, kind of the surface of the earth and tectonic geomorphology. Okay, so the key here is I want to explore this U sub R, this rock uplift rate, in a little bit more detail. So I'm going to move on to the next slide where we can define our rock uplift rate. What we're going to do is think about it in terms of two terms here. We're going to have our rock uplift rate that's going to be equal to our tectonically driven uplift rate. Hold on one sec. Oop, check something real quick. Yeah, I knew that was wrong. I got this should be a I've got a wrong sign here in my equation. So let's fix that real quick. Sorry about that, everyone. That was really wrong. That's why I tripped myself up there and stumbled. Okay. All right, we're back on track. So now we're still defining that rock uplift rate. And to understand how fast that mountain is going up, it's going to be equal to our tectonically driven uplift rate plus our isostatic uplift. Okay? So what does that mean? That means that if we've got kind of a plate boundary here, so your classic plate boundary, and then kind of have some mountains coming out of our plate here. This is our mountain, and we want to understand how quickly the rocks are lifting up. What's happening is our plate that's going down, um, we're going to have essentially some amount of uplift of the mountains that's going to be equal to um, just the force of the tectonic uplift, the pushing and faulting that faults up the mountains along faults. But also, if you're thickening the crust at the same time, you might also have uplift through isostatic uplift as well. And so isostatic uplift plus tectonic uplift together equal our rock uplift rate. Okay? Let's look at the figures from the textbook to kind of think about this in a little bit more detail. So if we just look at kind of rock uplift alone, this figure on the left here first, that we've got a mean elevation, and here's our marker bed here. And if we have our rock uplift, so we force those rocks up, then we'll end up with a higher elevation. So in this case here, just rock uplift rate is really high and your elevation is growing over time. However, let's think about this in terms of erosion and let's have an erosion rate that's equal to a rock uplift rate. Okay, so in this case here, we're still forcing our mountains up, but at the same time that we're forcing them up, we're also eroding the mountains down. And so this becomes an incredibly tricky balance here to understand the relationship between a mountain range going up and erosion that's tearing the mountain down. Does that make sense? Like you could have a mountain range that's going up really, really fast, but if it's also eroding faster than you're pushing it up, your total mean elevation could be going down. How flippin' cool is that? This is the field of tectonic geomorphology, and this is what a lot of students, if they're interested in, they go out in this field and they do grad projects. They'll go pick a mountain range, they'll go to the Andes, and they'll try and balance these forces to say, okay, how fast are the mountains going up? How fast are they going down? Can we quantify what the net elevation change is over geologic time? So that's really cool. Um, and remember that erosion and uplift are not independent. They are going to be linked because of isostacy. Okay, so this is a way we can think about that uplift rate, our surface uplift rate, merging together. And we're not going to derive this equation. We're just gonna provide it for you here. This is a way for us to quantify that uplift rate in terms of erosion and isostacy. So our uplift is going to be equal to our erosion, which is just our erosion rate here. But this term over here accounts for isostacy, that isostatic rebound. And so the two new terms we're introducing here is the density of the crust versus the density of the mantle. And so we divide the crust by the mantle density, subtract from 1, and that's our isostatic factor in balancing out the erosion rate. So the erosion rate's cutting the mountains down. Isostatic uplift is bumping it back up. Okay? So you want to tear your mountains down, but every amount you tear them down, they're going to pop back up. So it becomes this nasty little problem then to erode the mountains away because they keep popping up. Isn't that annoying? This was that example of your of when you took your wood block in the bath with you and started cutting little bits off the top of it. The thing still pokes out of the water a little bit more because of that isostatic uplift. Okay. So we can solve this kind of generally then, right? Because we can we know the density of the crust and the density of the mantle. And so what this means is generally for every meter of erosion, for every 1 meter you lop off the top of the mountain, 84 centimeters of new mountain pops up. Isn't that cool? That means it's really, really flipping hard to get rid of mountains because they're thick. They've got these thick, thick roots. And as you start eroding the top, they pop up. My great example of this is the Appalachian Mountains. Is everyone here familiar with the Appalachian Mountains? Here in the eastern United States. I know we got a bunch of Westerners here, but yes, there are mountains on the east too. They're not as big or tall, but they're pretty substantial. So this is the Appalachian Range that goes all the way down to the southeastern United States up through Pennsylvania. And you can see these fold ridges here like you get in Pennsylvania, which are big, huge incline syncline features associated with with cores of these mountains. But we've got some elevation here. You know, these mountains are, you know, down here in the south. I think the highest point on the in the Appalachians is, I think, almost 6,000 feet in elevation. Carmen's shaking her head. Yes, thank you. I forget the name of the mountain down there. I don't know my southeastern geography that well, but we get up to 6,000 feet in height. Hey y'all, where's the closest plate boundary to the Appalachian Mountains? Right? We build mountains along plate boundaries.
Is it the Pacific plate and the North American plate?
I mean, yeah, like the Appalachian Mountains today are smack dab in the middle of the North American plate, right? There's a plate boundary way out here in the Atlantic, that the plate spreading center where you're spreading, we're creating new Earth, and we've got, you know, way on the other side of the country over here, we got the Pacific plate, but the Appalachian Mountains are nowhere near a plate boundary today, right? And that's what you learn in 101, right? You learn mountains occur at plate boundaries. Classic example, the Andes, the South American Andes, right? And we've got the Nazca plate subducting under the South American plate. Can't invoke that here. Well, what the heck? Where'd these mountains come from? They're incredibly old. This picture behind me right here, this is our plate boundary around 325 to 260 million years ago. And the details aren't particularly important here. But right here, this is kind of North America. And this was part of the continent Laurasia. And we had Gondwanaland, which is part of Africa today. And these two plates were colliding into each other. The details aren't important, but this is an old convergent boundary that created the mountain building event, the Alleghanian orogeny, that built the Allegheny Mountain, that created the Appalachian Mountains. That happened. The orogeny ended 260 million years ago. Now, I know if I had a time machine, the first time I would probably go would be to the last glacial maximum. I think that'd be really cool. But number 2 on the list, I'd probably head back to the Alleghanian here, because the Appalachian Mountains about 260 million years ago were probably a little bit higher than the Himalayas are today. They would have been mountains up at 29,000 feet in elevation. And so what we've seen over the past 260 million years is eroding away the mountains. And you guys did this in our first homework assignment, right? Where we turned off isostacy and you calculated how long it would take to erode away the mountains. And you came up with an answer on the order of tens of millions of years. So if mountains are just eroding away, the Appalachians should be long gone. Yet here, 260 million years later, we can't get rid of the bloody things. Why is that? It's because of that core of the mountain that was depressed down into the mantle is popping up through isostatic rebound. And so the mountains, as you erode them away, they just pop up, and we're down eroding the core roots of those mountains today. So once you build big mountains, it takes enormous amounts of geologic time to try and get rid of them. Isn't that cool? I think it's really okay. There's other fun things we can do with isostasy and landforms as well. We can do this not on tectonic timescales, but on glacial, interglacial timescales as well. You could say, hey, let's instead of a mountain range, let's stick a glacier right in the middle of a continent. And so you add a huge mass to the continent. And as you add that mass, you're going to down warp that crust down into the mantle. But interestingly, you get this flexural upwarping along the margins of that mass you put on the continent. And so as we down warp in the center, you can actually bulge out and increase elevations just outside where you load the mass on. Isn't that cool? Yeah. We think about these plates as rigid, but we actually get these really cool flexural strain features. So this is really, really important in lots of glacial settings and understanding kind of what's happening with elevations. Understanding whether you're down here where you've had down warping, or if you're on the margins where you've kind of pushed material up. So here's another example from your textbook. And so here we've got an ice sheet, and we load an ice sheet onto the continent and push down the continent down into the mantle. But then we'll have that upwarping along the margin. That actually allows you to basically create this basin where you can create a proglacial lake. And this is absolutely important for understanding the lake history in the Puget Sound lowlands as well, because of these bulges we get on the glacial margins. Now, the other really fun thing is that once you load a glacier onto a continent, it pushes it down, and you'll lower the elevation of the crust right under the ice sheet, and you'll pop it up along the margins right here. But once you get rid of that glacier, you reduce that mass, then you start bumping back up the elevations under that depression, and your full forebulges actually go down. Isn't that cool? So here, look at this is present day rates of post glacial rebound from, remember, we had that large ice mass, the Laurentide and Cordilleran ice sheets on top of northern North America. Look at this fascinating thing. We actually see today that right under the Hudson Bay is where we have the maximum amounts of uplift. Red on red, that doesn't show. But we're talking about, we have in some places, we have over 10 centimeters currently, presently today, 10 to 20 centimeters, where if you put a GPS out and measured the same point, in a year, it's going to go up 10 centimeters. No faulting. You're not going to get faulting. It's just this broad kind of, as mantle kind of fills back underneath the depression, it's pushing the land back up. Now, as on the margins of the glacier, the land's actually going down. So how cool is this? So down here in where we had marginal amounts of ice, we're actually seeing our elevations are decreasing. So if you put the GPS out, you're going to get, in some places right here, you're getting up to almost 10 centimeters where the ground is actually lowering as that forebulge is going back down. Fascinating, huh? So, interesting. When I lived right here, I used to live in Erie, Pennsylvania, and we were right on the zero mark. We were right in between on the middle, the middle of the seesaw where you weren't going up or down. The elevation in Erie wasn't changing. If you went north in the Lake Erie, the land was going up. If you went into the forebulge, say Pittsburgh area, the land was going down. Okay, so there's some other really important other places where we can do this as well. And so we can do this where we dump a bunch of sediment offshore. So where we dump a bunch of sediment offshore, we can depress the continent, and then you'll get this upwarping just back on shore. And you can actually have terraces and measure these terraces. They're actually increasing and getting popped up in elevation because of this upwarping. Another great place to do this would be in tectonic settings where you have a convergent boundary. And so where you're thickening the crust, like in a fold and thrust belt, you end up depressing the mountains right underneath the mountains, and then you'll end up with this forebulge on the inland side of your tectonic margin. So forebulge is really common, and then in between you get a foreland basin. So you can see this in the Alps. You can see this in the Western United States. This is really, really common. And I bet in Kevin's Cordilleran Tectonics class, you'll take this and like spend 6 weeks on this one diagram, but we'll just leave it at one diagram, right? Where we've got this forebulge here that's related with this isostacy and balancing effects. Okay, let me add on another fun complication. And that's thinking about, from a geomorphology perspective, what's really important is how quickly your elevation, or how quickly you're eroding material out of the mountains, right? If you can erode the material out, then you're reducing the mass in the mountains, and so your isostatic rebound can increase. So I love this diagram from your textbook that allows us to think about peak elevation in a mountain range versus average elevation over time. So we're gonna, you can't see much here yet, but that's what these two lines are gonna be. The red line is gonna be our peak elevation. Our blue line is gonna be our average. So here's our continental crust and the mantle, and this blue line right here, that's going to be sea level. So what happens is we've had some event that's uplifted a huge plateau. So we've uplifted this plateau, and because of that, all of a sudden we have a dramatic nick point in the landscape. So what are your rivers going to do? Because we've created this nick point, we've lowered base level, they're going to start to cut down. And so what happens is we start carving valleys in between our peaks through fluvial incision. And now we can measure our peak elevation, the highest point in the peaks, and compare that to our average elevation in the mountains. So let's say these rivers are very, very effective erosional mechanisms. What we can see is that over time, we can deepen our gorges, our fluvial gorges, by significant incision. By doing that, we're reducing the mass significantly in our mountain range. And what happens is because of that, you're going to get rapid isostatic uplift. And so because of that, our mountain peaks pop up and we end up increasing our peak elevations over time. But only the peaks, because our mountains are such effective mechanisms of erosion. If you look at the average elevation throughout the mountain range, the average elevation maybe has gone down a little bit. How cool is that? This difference between the average and the peak elevation in a mountain range. So in this case here, because we've had rivers, they just slice through and can really effectively evacuate all that material. Our peaks are popping up, but because we're lowering our mountains overall, our average elevation is going down. Now we can run this model forward in time again. And as we start the slow incision and we get to the roots and there's not as much crust anymore, we decrease the amount of isostatic rebound. So this would be really, really lots amount of isostatic rebound here. Then we slow that. And then now, as we slow that, and erosion now is taking over, both our peak elevation and our mean elevation are decreasing in time. We can watch over time our peak elevations versus our mean elevations in a mountain range. And so this is going to understand these variables, you're going to have to understand erosion rates and uplift rates to try and balance these out through time. So things like fluvial terraces become incredibly important markers in time for understanding these types of events. Okay. That's about where we wanted to get to. This is perfect. We've got just a couple of minutes left. And that's because on our lecture for Friday, we're going to talk about tectonic settings and the different kind of tectonic settings associated with glaciers. So being able to identify the different tectonic you're setting in is really important for kind of thinking about the landforms you're going to see in that setting. And so, the top picture here is an alluvial fan that's been offset by a fault. And here's another fault scarp here. And this is in Israel. Right here, we've got a fault scarp right here. And then this is a classic picture you probably saw in an intro textbook, which is this offset along this fence that's caused by a strike slip fault. So being able to identify faults is really, really important. And then our final picture here, this is a normal fault right along the base here, where we've had faulting and this block is dropping down relative to this block that's going up. And this is a classic example of Hebgen Lake in the 1959 earthquake in Hebgen Lake, which is just outside of Yellowstone, which created Earthquake Lake today. And just a little teaser, this is one of my favorite stops when I do Yellowstone trips. So we will be going to go see the Hebgen Lake Fault if we are able to go to Yellowstone on the Yellowstone trip this summer. Okay, So being able to identify these types of features is really important in the landscape, and they become kind of small scale important landforms associated with tectonic forces. So we've only got 5 minutes, so I want you to start this, and maybe you can, while you're reheating your cold burrito, whatever you're having for lunch, I want you to continue this. But I've thrown up a nice little KML file on the Canvas website, which is a hillshade of the Teton Range front. So it just covers kind of a nice area right here along the base of the Tetons, and it's in Google Earth. What I want you to do over lunch is have a look at that hillshade and see if you can see any evidence for faulting and fault scarps in the Tetons. Okay? So we've already talked about this location. I think maybe you guys remember in glaciers, we talked about these beautiful end moraines and lateral moraines that come out of the Tetons that create these beautiful lakes. That's Jenny Lake right there. And then I think that's Taggart Lake or something like that. So what I want you to do is start thinking about if you can identify any fault scarps based on the hillshade imagery, and then start thinking about timing. Can you constrain the timing of how old these fault scarps are? Now, obviously, there's two ways to think about timing of geologic events, right? We can talk about relative or absolute dating. You're not going out there and collecting radiocarbon dates, so I'm thinking about relative dating. Anything you can constrain when these faults might have popped off here in the Tetons. The Tetons are one of the most active mountain fronts in the United States. It's actually shocking we haven't had any big earthquakes there in historic times, but the Teton Mountains are screaming up in elevation. So that's what I would like you to do during lunch is kind of just, it'll take 5 minutes. It's a really cool data set. Just go up and down the Teton range front there and see if you can identify any evidence for faulting. All right. Well, great job, everyone. I hope you enjoyed it. I love talking about isostacy and tectonic geomorphology. So hopefully you took some old concepts and maybe put a new twist on it for you in terms of thinking about geomorphology, landforms, and surface evolution. So, any questions for me?
I have a question on the landform atlas.
Yes.
For the 5 landforms, are we supposed to, for each of them, are we supposed to find a point on the map for them, or is it only one of them?
Yeah, it'd be nice if you've got your glaciers, and then you've got a point where you've got an arête, you've got a point where you've got a lateral moraine, and a point where you've got an end moraine.
Okay.
Yep. Other questions?
Yeah, where do you want us to put the link for that?
There should be in the homework 4. If you click on the homework 4 and assignments, it should allow you to put a link right there.
Okay, cool.
Also, when is the landform atlas due?
It's due the day of our final exam slot. It says it on the final assignment link is up. You could turn it in tomorrow if you really wanted to, but it has the due date on it. I don't remember off the top of my head, but it is. I've given you as much time as I can possibly give you, which is our final exam period. Then I need some time to look at them because it's a quick turnaround on my end when I have to have the final grades. It's after Thanksgiving break. So what you can do is you can pull out your iPad during Thanksgiving dinner and show your family all the really cool landforms you're finding.
Lyman, do we have class during our final exam period or not?
Nope.
Okay.
Nope. If you've got lift ticket for Banff that day, don't cancel because of me.
No, another class wants to meet during that time. That's all.
How dare they? I mean, no, you have to come to my. No, fine. Anything else? All right, well, have a glorious lunch. I feel really sick from eating a donut, so I don't know if I'm going to have lunch, but see you guys soon. Bye.
Thank you.